In the name of Almighty God, I am Master Sankoshi, and today I want to continue for Physics GRE Radiation chapter. Since moving electric charge can create electromagnetic waves, and these electromagnetic waves carry energy, it is possible to produce electromagnetic radiation far away from the charge. Indeed, the accelerating point charge radiates the total power as follows, where Q is the charge of the oscillating particle and R is its acceleration. The two forms are related to each other by equation 2.60. This formula, known as the Larmor formula, only holds when the charge is moving at small velocities, when v is very smaller than c. The prefactors are not so important. What really matters is the q to the power of 2 and r to the power of 2 dependence. An oscillating dipole will also radiate, and in fact, this situation is more common because most molecules in nature are dipoles rather than free charge. Let the dipole have dipole moment. PhD is equal to B0 cosinus omega t ZP. There are two useful formulas here. The first is the intensity. Intensity is equal to micro zero P0 to the power of 2 omega to the power of 4 divided by 32 multiplied by P to the power of 2 and C multiplied by sinus to the power of 2 theta divided by R to the power of 2, where theta has its usual meaning in spherical coordinates. As usual, don't worry about the numerical factors, but what is important is the p0 to the power of 2 dependence, the same as the q to the power of 2 dependence in the Larmor formula. The frequency dependence, omega to the power of 4, the fact that s falls off as 1 to the divided by r to the power of 2, and the sinus to the power of 2 theta term, which means that no radiation occurs along the dipole axis, and it's mostly can be because of the uh, barrier that is on the radiation. Integrating based on the 267 over a sphere of radius r gives the total power. P is equal to micro 0 p0 to the power of 2 and omega to the power of 4 divided by 12 pc, which has the same p0 to the power of 2 and omega to the power of 2 dependence. By the way, the reason we deal with dipole radiation rather than monopole radiation, for example, a sphere of charge with an oscillating radius, is the curious fact that monopoles don't radiate. This actually follows from the Gauss law, which says that the distribution, Gauss law is actually talk about the distribution of the electron on the surface, and it's not dependent on the surface geometry, the size or its geometry, which says the field outside a spherical symmetric charge distribution is independent of the size of the sphere. The above formulas applies to electric dipoles only. There is an analogous formula for magnetic dipole radiation. PAB is equal to micro 0 m0 to the power of 2 omega to the power of 4 divided by 12 p c to the power of 3. Now I'm gonna go through the circuits. Depending on the flavor of your undergraduate education, your knowledge of circuits might be a little rusty. One of us actually never learned circuits in an undergraduate course, possibly because they were deemed too practical and don't and not of fundamental importance. Apparently, the GRE doesn't share this opinion, so it behaves you learn this material, such as the resistor at the this figure 220, symbols of three fundamental circuit elements as RCL. You see that R is the resistor, capacitor, and inductor. Well, thankfully, it's not too difficult at the level of the GR test. Basic elements. There are three fundamental circuit elements: resistors, capacitors, and inductors. Their icons, the circuit diagrams are shown in figure 2.20. The voltage across each element are given by VR is equal to I, or current multiplied by resistance. VC, or capacity voltage for capacitance, is equal to Q, or charge divided by capacitance, and voltage in inductance, or L, is equal to L, which is a constant for inductance, and the derivative from the current divided by time, where R is the resistance, units of ohms, C is the capacitance, units of farads, and L is the inductance, units of henries. When confronted with a circuit journalist, one typically wants to find the current or voltage across some element. For simple circuits, this is done by subdividing the circuit into the equivalent blocks and computing the total resistance, capacitance, or inductance of each section. The practical formulas for adding elements in series are, for if we make it as a series, is R resistance is equal to sigma. The lower boundary is I, the number of resistance, or I as a series. And if we have a series for capacitance, we have a inverse. We have 1 divided by capacitance total is equal to sigma I, is a total of the capacitance and series. And if I want to sum up the whole and total of the inductance, is L is equal to sigma I, is a lower boundary, and Li as a series. In parallel, we have the rules. The first rules, we have the completely inversely from the series. When we add these elements in a series, is completely inverse from the parallel. For example, here in the resistance, we have directly, it has a directly sum of all of the resistance, but just the capacitance is inversely. You see that here is completely different. When here we have a sum of the resistance, here we have a 1 divided by total resistance is equal to sigma I, is lower boundary, I 1 divided by Ri is parallelly. For parallelly in resistance and inductance, we have an indirect sum up, but capacitance is directly sum up. It's completely inverse from the resistance and capacitance and inductance sum up in the series. So series is completely different with parallel. These rules come from the fact that circuit elements in series see the same current, while circuit elements in parallel see the same voltage, while capacitors and inductors are created by very particular geometries of conductors, and wire resistance is a property of all materials. More precisely, we define a material dependent intrinsic property called resistivity. The resistance is the impedance to electrical current for a particular geometrical configuration of a material. The general relation between the resistivity rho of a material and the resistance of a geometry is given by R is equal to rho L divided by R. Rho is a density, L is a length of the wire, divided by R is a cross-sectional area, where the R is the cross-sectional area of the resistor and L is the length. Now I want to go to the Kirchhoff rules, a more general method for solving for currents and voltage in a circuit is to use Kirchhoff rules. This method is more systematic for larger circuits, but it leads to a system of linear equations which can be cumbersome to solve quickly on GRADs. There are two rules which are consequences of conservation of charge and energy respectively. The first rule says the sum of currents following into every node must be zero. The next rule is the sum of the voltage across elements around any closed loop must be zero. So the first rule of the Kirchhoff rules says that the Sum of currents must be equals to 0 for every node, and for voltage in every closed system and closed loop must be 0. The strategy is then to write an equation for every node and loop in a circuit and then solve them all simultaneously for the desired current or voltage. Since they are so systematic, Kirchhoff's rules are good to use when you are uncertain how to solve a problem using the series and parallel circuit rules above. Now I'm gonna go through the energy in circuits. An important distinction between the three circuit elements is between dissipative elements and elements that conserve energy. Resistors dissipate energy according to the famous rule when the P is equal or P is a power is equal to I as a current multiplied by voltage is equal to voltage to the power of 2 divided by resistance is equal to I or current to the power of 2 multiplied by resistance. And this power usually shows up as heat, which rises the temperature of circuit elements, which is why the back of your computer gets hot. In contrast, capacitors and inductors don't dissipate energy, but store in electric and magnetic fields. As we have previously discussed, we will repeat the formulas here for convenience. So the power or energy is UC for capacitance is equal to 1 divided by 2 capacitance voltage to the power of 2, and for inductance we have UL is equal to 1 divided by 2 L or sum of the conductor inductance I to the power of 2. Now I want to go through the standard circuit types. Circuits generally have two kinds of behavior: transient, which describes charge and currents that die off quickly with time, and a steady state, which describes the state of the circuit after a sufficiently long time has passed. When analyzing circuits that contain a combination of different elements, the transient as opposed to steady state behavior of the circuit is very important. The general approach for analyzing such circuits is to write down the voltage around some section of the loop, for example using Kirchhoff's rules, and then use the relations in equation 2.70 and 2.72 to produce differential equation in current or Q as a charge. You can then solve the ODE with exponentials to extract the time dependence. For more qualitative but very useful discussion of the time behavior of circuit elements, see section 7.3.1. I will go through the RL circuit. Consider the example of a circuit with resistors and inductors in series with a voltage source. The circuit satisfies the equation V is equal to IR plus L multiplied by the differentiation current based on the time. If the voltage source is suddenly switched on, the current is I is equal to V divided by R and multiplied by 1 minus e to the power of minus t divided by tau RL. The time constant or tau RL is equal to N divided by R is the characteristic response time of an RL circuit. All transient behavior of RL circuits with DC voltage is exponential, which is characteristic time. Now I'm going to go through the RC circuits. The situation with RC circuit is very similar to RL circuit, and RC circuit is a circuit containing resistors and capacitors in series and possibly a voltage source as well. The equation of current of an RC circuit with no voltage source is 0 is equal to R multiplied by dq divided by dt plus 1 divided by C multiplied by Q, or charge. The discharge of a capacitor in such a circuit or the charging of a capacitor in a circuit with a voltage supply is again exponential with characteristic time constant, which tau RC is equal to RC. Now I'm going to go through the RLC circuits. Combining all three basic circuit elements gives the most interesting elementary circuit. The RLC circuit, happily, the mathematics of this situation are identical to the problem we have already treated, namely masses and springs with friction. Just refer to table 1.1, section 1.7.3 and make the appropriate substitutions. Note that an LC circuit can be considered a special case where the resistance R goes to zero. In that case, the resonant frequency of the circuit is omega 0 is equal to 1 divided by square root LC. Thank you so much for watching. My tutorial will go to the end. Today is 26th of April 2026 and time is 11:11 p.m.